records automatically. Let me start again, right? Good night from Bloomington, and this is another Tuesday. Run regressions we do, and study econometrics we will. And yeah, I see it recording now, and thanks for letting me know, because that's what we really need, right? The recording, because not everyone can make this time. And also it's March Madness. I don't know, maybe some of us are just watching the games rather than watching me talking about business econometrics. And thank you, Ryan. Yeah, it's a good catch. And by the way, the midterm is next week, but the thing is, it starts on Monday, but in my experience, not everyone is gonna take, or not a lot of the students will take on Monday or Tuesday, right? I am gonna cover midterm material on the next live session, and then or can I do this on Monday? How about this? Maybe for a week, special to the midterm, I move the live session to Monday evening rather than Tuesday evening, so that if you would like to take the midterm on Tuesday, you can, and you know, it saves you one day, kind of. How would that sound? I know there are only 10 of us here, but okay, let me take a note. Because Monday I teach all day. I start around 11 a.m. until 5:30 p.m. But we can meet around 7 p.m. again on Monday, and we can talk about more on multiple regression models to finish the topics and also the midterm, and I will answer your questions. How does that sound? Monday, 7 p.m. Business econometrics live session. Usually I run my live sessions on Mondays or Tuesdays, but this Monday, or this semester Mondays, I teach back-to-back too many courses, and I don't want to be really talking with you in a tired manner. I want to have the full energy, but next Monday we will meet, because there will be the midterm next week, and I will be answering your questions. Exactly. What we will cover next Monday is gonna be in the midterm as well. And in fact, I was trying to see if I could cover everything today, but I just couldn't see the way, because there was a lot of things to cover in a way. For an hour or even 75 minutes, it wouldn't be enough. But if you don't have any questions, right, let's start. And here's what we did last week. Previously in business econometrics, we started to look into the multiple regression. We went on with some examples, and then we saw how we run multiple regressions on Excel. And at this point, is every one of you capable of running a regression on Excel? You use the data analysis and solve for the regression model, see the regression option, and then analyze the intercept and the slopes. Do you feel comfortable with the Excel model? How to run regressions? Okay, that's good. That's good. It's something you may need or may not in the midterm as well. Because in the midterm, what I'm planning to do is, rather than giving you the data or so, maybe I'll give you the output, because running the regression is not the difficult part of this course, right? You can just click on the regression and arrange, and then you'll end up with the regression. But what if I give you the output, how to read the output from the Excel and run the hypothesis tests mainly, right? Which we will cover today. And tonight, what we will do is, we will take a look at the omitted variable bias very quick. I will solve an example with you, and we're going to discuss what the omitted variable bias is. And we're going to look at the distribution of the OLS estimators. By OLS estimators, what we mean is beta 1, beta 2, beta 0, right? The parameters that we are estimating, and with the classical linear assumptions, how can we test the real values or not. So we're going to introduce the hypothesis testing and also some examples tonight, and hopefully you will know how to run two-sided, one-sided tests, and also how to test single linear combinations of parameters. So after tonight's live session, you will feel comfortable with running regressions and tests the parameters, whether the true values are the given or not. So let's start with the omitted variable bias, and let's go back to the theory, what we are suggesting, if there exists a bias or not. Now we have the regression model. What do we mean by the regression model? At this point, our regression model is the linear regression model, where we have the y dependent variable, which can be explained by the set of the independent variables. But if there is a relevant variable and you are not including, then the model is underspecified. Then we can tell how the missing variable is affecting the model or not by checking the omitted variable bias if we know what the omitted variable is. But here is the theory. I just did this very quick last week, but let me go over it again. If we have a parameter like y, right, and we believe that y is explained by x1, this is a simple linear regression model. But what if we are omitting a very important variable, which is x2? But where is this x2? This x2 is within the unexplained part, right, in this first model. If this is kind of an important variable that adds more value into our model, then we can claim that excluding the variable must matter, because when we exclude the variable, the exclusion will create a bias on this beta 1 tilde. Then we may end up with wrong expression and our model would be wrong. In order to get the right effect, how y is changing with x1, we may need to add x2 into our model so that we explain better. So let me give you an example what I mean with the data, but I'm going to keep my example very simple, working with the data, and I'll show you how the bias is created, especially when what we are omitting is a kind of an important variable that explains what's going on in the real world, right? So here is my example. Now, if you click on the hyperlink, you can find an article suggesting never drink Diet Coke. Diet Coke is for fat people. What do you think? Do you drink Diet Coke? The study shows, the study on the news, on the link, shows that if we take the people who are drinking Diet Coke, these people are gaining weight, and that means Diet Coke must be for fat people, and you are getting fat when you drink Diet Coke, which is a contradiction, right? Because the promise of the Diet Coke is you drink and less calories and you gain less weight, right? Rather than drinking the red one, right? Or this one, right? Red one, this one. By the way, I like the taste of this one. I don't like the taste of Diet Coke, but I believe Diet Coke is not for fat people. But how can you test this? Actually, this is a question, right? Does drinking Diet Coke cause weight gain? Can I check that? Can I test that? If I have the data, depending on the weight and the consumption of Diet Coke, then I can test that. However, you come up with a theory, right? Possible theory could be the material, like the ingredient aspartame in Diet Coke, instigates weight gain, right? It could be a possible explanation. But your model may be wrong. By the way, is anyone here Diet Coke fan? I had a colleague, in fact, I have a colleague, I still do, so I have a colleague who likes to drink at least 1 Diet Coke per day, and in fact goes 2, 3, but he goes always for 1. But he's not fat at all. So how can we check? Here is what we're gonna run. Coke Zero. Justin, quick trivia. Do you know why Coke Zero is introduced or was introduced? Does anyone know? Paul, do you know? No clue? No? Okay, Coke Zero, Diet Coke. Diet Coke is introduced for everyone, but after some point, that's right, Jay, after some point, how happened, I don't know, but only females, like ladies, started to drink Diet Coke. And the guys thought it was feminine, right? I'm not gonna drink Diet Coke because it makes me feel more like feminine rather than muscular, right? So then Coca-Cola realized that they are not gonna sell this Diet Coke to males, and they came up with the more muscular image, like the black, red, and then more tougher image of Coke Zero, right? But basically they're the same, but only the packaging and advertising. Okay, so that's why. Now you know. I'm sorry about that. So perhaps what we will do is we run body mass index, which is kind of showing us how fat you are, right? Do you know what your BMI is? Quick trivia. Then we run this in with a model of the Diet Coke consumption. So let's go to the spreadsheet. Now let me share my spreadsheet with you. Can you see my other screen now? Okay, so here is what I have as the data. I have the body mass index and I have the Diet Coke consumption. Okay, so that consumption is basically, you know, this is something I generated, but anyway, this could be the number of cans per monthly, right, in a year. So multiply this by 12 and you'll get the total consumption per year, something like that. Okay, so what we want to do is first we want to run this regression and see how the slope and the intercepts are, and then we interpret, right? So what we would do is choose data analysis regression to save some time. I did this before. So this is the first regression. We are regressing body mass index on Diet Coke. So what do we see? First, we see that given the observations, there is a positive effect of Diet Coke. And in fact, if we just run this data is suggesting if you if you drink more Diet Coke, then your probability of gaining weight, like body mass index, increases. Like what? For one Diet Coke consumption, your body mass index increases by 0.013 or 0.014. So there is that positive relationship between Diet Coke and body mass index if we only run the regression with one parameter. But what if we are omitting something? What could be relevant and very important that we are omitting? Can you tell me? Because that's what it is going to create. What it's going to create the omitted variable bias, because all the others within you, there may be many other factors that affects the model itself. Exactly, right? The eating habit or exercising habit, how the habits of the person is, because right now what we are only controlling is the Diet Coke. And if you remember the assumptions, what we are assuming is whether you are a fat person or whether you are eating many calories or less calories, or whether you are exercising or not exercising, your consumption of Diet Coke remains the same. There is no effect on that. But would that sound right to you? Would that sound right to you? Like, I eat more or less, I drink the same Diet Coke. Not at all, right? So one of the assumptions is not going to be satisfied. So this model would be wrong. So our estimator would be wrong. So how can we understand the bias? Here's how we are going to study the bias. Let me share my other screen with you now. We're going to check the following. We're going to include the omitted variable, and we're going to check what the effect of omitted variable is to the model, but also we would like to see how the two are correlated. It's like if we're gonna add whether you eat calories or not, how is the correlation between eating calories and drinking Diet Coke? And you cannot imagine how many times I see these like little bit overweight people drinking the huge Diet Coke, but with 2-3 sets of fries and 2 hamburgers. You cannot imagine. And in fact, you may not get the calories from the Coke, but you know, 1 set of fries, do you know how many calories is 1 set of fries? Yeah, here, Paul, I want you to make an exception because this data is something I didn't really fit. I just generated randomly. Okay, that's why R square being 10 is practically, this is 10 because there's a reason for that, because we don't have enough information, right? It's not gonna be really up, okay? Because body mass index can be explained with many things, and only Diet Coke is gonna really explain the 10% of what's going on. Yeah, way too many of them, but it tastes so good. And you know what they say, if something is bad for your health, usually it tastes good. And if it's good for your health, like it tastes really like, I'm not gonna say it. Okay, you understand what I meant, right? So sometimes that is the case. So let's do this. Here's what we're gonna look into. But right now you are seeing my slides, right? My slides on my other screen. Okay, perfect. So conceptually, we're gonna look into what drives the omitted variable bias. Here is what we're gonna do. Suppose we have a variable x1, like this is the Diet Coke, okay? Just a second, let me take my pen. So this x1 is our Diet Coke that we believe positively impacts y. So drinking Diet Coke positively is impacting the body mass index. So that means when Diet Coke is increasing, y is increasing. That's what we found out, right, from the data. But suppose there exists another variable x2, and that is what I'm gonna call as the sugar calories. You eat sugar. But that like sugar calories, like corn, fructose sugar, like what is it called? I can't remember. My brain, like high fructose corn syrup, like it. You know, we eat that everywhere, even if you don't want to. It's everywhere. It's inevitable. So if that is the case, and it also positively impacts y, which makes sense, right? If you eat a lot of sugar calories, then it's gonna impact your body mass index. But if it moves in the same direction with x1, like if you eat more sugar calories and because you are eating more sugar calories, you want to compensate with Diet Coke, then they are gonna be correlated, so it's gonna create the bias. So what we're gonna do is we regress y on x, that's what we did, right, at first. Then what we need to do is we need to see how the correlation is. So what we're gonna do is we will try to see what if x1 and x2 are correlated, is it gonna be a positive impact or a negative impact? But in the model, if it's positive impact, then it means it's overstating the x1's effect. Here's the thing. We believe that you drink Diet Coke and your body mass index goes up, right? But that's not right. You eat more sugar calories to compensate. You drink more Diet Coke, but your body mass index increases not because you are drinking more Diet Coke, but because you are eating more sugar calories. So omitting that variable is going to create bias on our beta 1 parameter, which we found positive. Am I making sense here? Any questions? Is my logic making sense to you? How the omitted variable bias can underspecify the model? Okay, so what we're gonna do is, oops, before we do that, let me share my other screen with you. Let's run the other regression and let's see what's gonna happen. Okay, you'll tell me. Okay, so what we have is now the independent variable as body mass index. The dependent variable says Diet Coke and sugar calories. I run now the multiple regression model, and here's what I have. The multiple regression model as now, what do we see? We see now the Diet Coke has a negative effect, but sugar calories has a positive effect. And in fact, in our first model, we were overestimating the parameter beta 1. And in fact, in this model, what we are doing is we are basically saying the body mass index increases because of the sugar calories, and in fact, Diet Coke has a negative impact because it compensates. So what we want to do is, what we want to do is basically to run another regression to see how these two are kind of, where is my, okay, these two are kind of correlated or not. So let's see that. We are going to run another regression. I'm going to run, so I'll do this here. I didn't do that before. So I'm going to run this first. So it's 6764. Then on C, 6764. So what I'm doing is I'm running a regression seeing how Diet Coke is correlated with the sugar calories. So let's run that. Oops, why is it wrong? Oh, how many data do I have? I'm sorry, just what's my data points? Oh, 1101. I'm sorry about that. So let's run the regression. Okay, is it a nominal data? So body mass index comes from your weight and height, and the Diet Coke is like your average consumption per month. Okay, that's what the Diet Coke is. So let's 1101 and 1101. Okay, so what do you see? You see that now they are almost perfectly correlated, right? And what you see is there is this positive correlation, and what we see is Diet Coke consumption increases when sugar calories are consumed more. So people who are eating more sugar calories are more likely to drink Diet Coke. That's what it is saying basically. So that creates positive and positive bias. And if we go back to our first regression, what we have is this 0.158. That 0.158 is too high. So we are overestimating the impact of Diet Coke on body mass index. But when we include the omitted variable, we are correcting for the bias, and the right model becomes Diet Coke consumption in fact helps you to lower your body mass index, and that's what the bias, that's when the bias is created. And in this example, I tried to show you the concept, but you can apply this concept to any parameter you feel like it's important and you are omitting. All you need to do is to check the following. Let me share my screen with you. Following. You check the coefficient in front of x2, the omitted variable, and you check the correlation between the variable versus the omitted variable. If they're both positive, you create a positive bias. If you are both negative, negative means you are creating again a positive bias. If one is positive and the other one is negative, it creates a negative bias. And I strongly recommend you to understand this conceptually, okay? How the omitted variable bias can change or underspecify or overspecify the model we are estimating. Because in the midterm, I can tell you, I may ask you conceptual questions on this, omitted variable bias. So before we move to the second part of today's live session, do you have any questions? Is the example clear? Diet Coke is not for fat people, and in fact, when fat people are drinking Diet Coke, they are compensating the weight gain, kind of. So it helps, right? So that's what we are proving here. So yeah, it is a positive bias, which means when you are omitting the variable sugar calories, that positive bias is increasing the effect of Diet Coke. So from negative to positive. So that's the positive bias. Does that make sense? It's increasing that parameter from negative to positive. Yeah, that's right. But seems all things equal, any soda would not favorably impact BMI. You know, Diet Coke not in our model. So we cannot say, but anything keeping constant. Is that what you're saying? Like, okay, let me show it. Let me share my screen to you. Okay, what we did is we run the first regression. Here's what we have. This is our beta 1, 0.15, right? Then we run the same regression, and now we have the parameter beta 1 as negative 0.09, and in fact it's like negative 0.01, right? Negative 0.1, I'm sorry, negative 0.1. So the difference between two, negative 0.1 to 0.15 is the bias, and it's a positive bias because we are increasing this beta. So that positive bias is over specifying the parameter to 0.16. The right value is negative 0.1. Does that help? Is it better? Is it fair to think about like sugar calories are lumped in with Diet Coke incorrectly? Once you break out sugar calories, we actually see that Diet Coke is related to lower BMI. Yeah, that's what basically the explanation is, right? And also in our model, Dan is right, we have the relationship between the Diet Coke and sugar calories. If they were not correlated, then you would be right. Alone, Diet Coke would not improve BMI. Yeah, alone, Diet Coke would not improve BMI. What value is, oh, correlation? So we are not just checking the value, but we are checking the positive or negative. Like if the correlation is positive or negative, and we run the regression, this regression, where's my other regression? Here in regression, right, you see R square is almost 1%, 100%, and we check the coefficient, and that means these are like very correlated, right, positively correlated. So that gives us the positive correlation and positive beta 2, so positive bias. But of course, what you can do is you can use Excel to find the correlation itself as well. Okay. Makes sense? Okay. All right. So let's continue with hypothesis testing. You already know what the idea is, right? We are basically testing if the right value we would like to know is within the confidence interval or not. That's what we studied in the very first weeks. And then this is what we're going to do. We're going to apply the idea into our estimates. So what we need is we need some set of assumptions so that we can run the hypothesis testing. Yeah, Paul, you're right. This is only relevant if R square is very high, like correlation. But of course, if R square very low, you are not explaining really. These two, maybe the omitted variable is not really creating the bias, right? So you may want to omit that variable. Okay. So we stated the 4 assumptions last time, if you remember. We believe that our model is linear in parameters. By the way, okay. You are seeing my slides, right? I'm switching back and forth, so, okay. So we believe that our model is linear in parameters. We believe that our sample comes from random sampling. So we have no perfect collinearity, which means we cannot write any independent in terms of the other independent. We have the zero conditional mean, so whatever we are omitting within U is not really changing the behavior of the independent variables, right? That's what it means. Then we're gonna add 2 more, homoscedasticity. Homoscedasticity is about the variance. It's very technical, but with this assumption, what we are assuming is the variance of the points are like independent, so they are basically fixed. The variance of the errors is fixed, and normality is what we are assuming is the parameters are distributed normal. But what are these assumptions for? When we have assumptions 1 to 4, we have the OLS estimators as unbiased, no biased, so there is no omitted variable or anything, right? Our estimators are unbiased. So on average, they reflect the true parameters. When we add 1 more, number 5, homoscedasticity, then that means not only our estimators are unbiased, but these estimators are the best linear unbiased estimator, blue. So there's a theorem behind that, and that Gauss-Markov theorem is basically suggesting when you have the homoscedasticity, you cannot do better than the estimators that you are finding. But when we add the normality assumption as well, what does assumption number 6 do for us? Can you guess? When we assume the distribution of these random parameters, beta 1, beta 2, beta 3, beta 4 is normal, we can apply hypothesis testing, and we can see if the value we would like to question is the real value or not, or we can see within some confidence interval is our value in question in the interval or not. Exactly, we would like to end up with the standard normal distribution, right? That's the idea. So with assumptions 1 through 6, what we have is the OLS estimators are the minimum variance unbiased estimators. So we have the most efficient estimators combined, and when we compare with any other unbiased estimator, not just a linear one, this is gonna beat every other one. So it's the most efficient one. That's what we want to work with. We can now conduct hypothesis testing. But what we know is when we are conducting hypothesis testing, if the population is known, we use normal distribution, right? If it is not, then we have t-distribution. But once we made assumption number 6, we can run these tests. But if we don't have the assumption number 6, then we cannot run the hypothesis testing. Then we have to come up with another methodology. So we are assuming these 6 hold now, and assuming 1 through 6 holds, then what we have is the random variable beta j hat is gonna be distributed normally with mean beta j and variance beta j hat. Okay, this is what we estimate, beta j hat. But what is this beta j? Can you tell me? If beta j hat is the estimate, the mean, so if this is the case, what would be the mean? Like, you know, if the estimator is unbiased, what is the expected value of beta j hat gonna be? 0? No. That's beta j x minus, What I'm asking is this. Exactly, sample mean, so it's gonna be beta j. But if we believe 1 to 6 holds, this is gonna be the true value. Point estimate, right? That would be our point estimate. And we're gonna transform the distribution. If we have the random variable minus the mean divided by the standard deviation of the random variable, it's gonna be standard normal. Do you remember how we transformed the normal distribution to standard normal? That's what we are doing here, and that's what we will be doing when we are coming with the test statistics and we run the tests. But we are applying the rules of statistics here. We are trying to see if the value in interest is gonna be within our confidence interval or not. Here's what we're gonna do. We're gonna run the regressions, and then we're gonna ask, let's check, right? What if the true value is 0? So we're gonna switch this beta j with 0 to check if the true value is 0 or not. Or what if true value is 15? What if 20, right? So we are gonna see if 15, 20 is within the confidence interval or not. There's your 0. Yeah, there is always somewhere 0. 0 is in fact a very, very important number, right? If there was no 0, probably the math would be so different. Like 0 is the starting point, like the origin. But is what I'm will be doing clear? Like, is what I'm doing here clear? Like transforming into standard normal and check if the value in question is within our parameter or not. But let me show some examples, right? Should I? Okay, let me mention these points as well. So what we are interested in is the standard error of the random variable, because we wouldn't know the standard error of the random variable beta j hat, but then if we run the regression model OLS, the Excel will tell us what the standard error is going to be, and we will have the distribution as the t distribution with n minus k minus 1 degrees of freedom, where n is the number of data points we have, k plus 1 is the number of parameters we are trying to estimate. Like if we have beta 0, beta 1, beta 2, beta 3, beta k, that means we have k plus 1 parameters that we are trying to estimate. And then that makes only n minus k minus 1 degrees of freedom. That means what? Okay, here is the degrees of freedom idea. Here, let me give you a very simple example. Let's say I am trying to estimate one number, right? Or I'm trying to estimate the numbers. Let's say, okay, here's how I know. Okay, let me put this way. Let's say there are 3 numbers. Okay, 3 numbers. And what I'm telling you is the sum of 3 numbers is 100. What's your degree of freedom? How can you choose freely? How many of the numbers can you choose freely? That's how degrees of freedom works. I'm telling you, like a puzzle, right? I'm telling you, there are 3 numbers. Right now, it's like I'm writing down 3 numbers here. And what I'm telling you is, if you want to guess what numbers I'm writing down, what is your degree of freedom to choose? Can you choose 3 of them freely if the sum is 100? You cannot choose 3 but 2, right? Because if you pick 50-50, the third one must be 0, right? Or 15 and 15, the third one should be 70. So in fact, your degrees of freedom is only 3, only 2, because you know the sum. And that's the same way. If you know all the parameters, k plus 1 parameters, and you have n points, then your degrees of freedom will be n minus k plus 1, because you already know k plus 1 thing. These are the constants. And that's why we have the degrees of freedom as n minus k minus 1. Okay? Having said that, we are ready to solve some examples, and I'll show you how these hypothesis tests will be run. Here's my model. I would like to know how you price your house. And I believe that this is the right model and all 6 assumptions hold. And what I have is house price depends on the number of bedrooms. Would you say it makes sense? The number of bedrooms. Also the lot size. Also the square feet. And in fact, you know, given my kind of background, I'm a little bit suspicious for this model, because here is why. What I'm suggesting is I would like to know the effect of number of bedrooms given the square feet is the same. So what would you suspect, positive or negative, given the square feet is the same? Number of bedrooms, is it gonna impact positively or negatively? But then you have to ask this question, all right? What if you have 1,000 square feet? 1, 2, 3 would be fine. But what if there are 10 bedrooms? Is it gonna affect still positive? No, right? So this is basically telling me that this model is not gonna explain everything, because maybe there is not first order, but we may want to add more into this, like bedroom times square feet, or even square feet square, or maybe even bedroom square, to see the second order effects, to see how the function is changing. But I'm gonna keep my example simple to show you how to run hypothesis testing rather than to explain how the housing prices are read. And in fact, something I'm not putting in here, but it really affects the housing price. What would it be? It is not here. Exactly, right? Location, 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 the neighborhood, the schools and everything. So there will be always an omitted variable bias here. But let's assume this is the model we believe in, and assumptions through 1 through 6 holds. But in the real world, it wouldn't. You need more data to show the real house prices. This is not enough. But let's assume this is enough. Okay? So given that assumption, let's start with the classic tests. Classic tests are two-sided tests and one-sided tests. We're going to run the regression, and I'll show you in a moment. But what we're going to do is we're going to check if some beta is going to be equal to the value in interest or not. And then that's a two-sided test. We already have studied the two-sided tests. So what we will do is we will have a normal random variable, beta j hat, and we will know the value of this, right? The value of this beta j hat comes from the regression. Then we have a hypothesis value for its mean. This is the number we are interested in. So this is what we will come up with, that number. Then if the hypothesis is true, we know the distribution when we subtract the beta j hat from C, which will be the t distribution with m minus k minus 1 degrees of freedom. Then we observe a realization of the random variable. We're going to ask if the standard value is reasonable if the null were true. So that's like the process. That's how we're going to run the hypothesis test. And then we will come up with the test statistics suggesting beta 1 hat minus C divided by the standard error beta 1 hat. And with the regression we're going to run in Excel, we would know these values, beta 1 hat and standard error of beta 1 hat. And then come up with this number, so it will be a number. Then we're going to check with the critical value. How can I get the critical value? Can you tell me at this point? Critical value. How would you find the critical value? Because we have to check whether exactly we need the t-tables. Also, we need the alpha, right? What is alpha? Are we looking for 95%, 97.5%, or 90%? So we're going to check that. And if you are ready, I think I can show you like what we are doing here. So we're going to choose a significance level. Why is this going like, okay. So we're going to choose the significance level. That means that we are building a confidence interval 95%. And if this is a two-tail test, we want the area of each tail to be alpha over 2, like 90. We want each probability to be 0.025 and 0.025. And then we will be checking on whether the value in interest, like test statistics, is within the confidence interval or not. If it is within these range, would you reject or fail to reject the null hypothesis? If it is within, You fail to reject, right? Because the out tails are the rejection ratio. So you fail to reject means the value in interest could be, in fact, statistically significant. One-sided test is pretty similar. So you come up with the test statistics, but only thing is now the area is 0.05. So you have only one tail rather than two tails. But we still check if the value is over, test statistics is over the critical value or less than the critical value. Okay, let's go to the spreadsheet now and see how the regression is, and then we're gonna run some hypothesis tests. Are you ready? Let me share my other screen with you. So where's my other Excel? Okay, right here. This is the data I have. And in fact, I have how many data points? 88. So let me run the regression very quick. We are all doing the same thing, right? Data analysis, regression. I choose my input, and then I choose the others. Then here we go. This is what we have. And the data is suggesting there is positive effect of the number of bedrooms, the lot size, and square feet. They all positive impacting the housing price. And in fact, number of bedrooms is impact by 13 in thousands. House prices on thousands. Okay, so this is what I have with the data, like 300,000 for 4-bedroom, lot size 6,126 with square feet 2,438. But as I told you, this is not gonna be the right model really, because we need location, the neighborhood, even the schools, many more, right? This may create omitted variable bias. But let's use the model to run some tests. Here is my first test. Oh, you don't see my slides, right? Okay, maybe I'll bring my slides back in here. Okay, just a second, because I want both. Okay, I'm moving my slides right here so that I don't have to go back and forth. Okay, you can see the slides now, right? Not as a PowerPoint presentation, but as the slides. Oops. Okay, here's my claim. What I'm claiming is adding a bedroom adds 50,000 in expected home price. But what am I testing? Can you tell me? Which variable here, in fact, is my random variable? Is it this, which is beta 1, right? Or beta 2 or beta 3? And my claim is adding a bedroom adds 50,000 in expected home price. Which one? Beta 1, beta 2, beta 3. Beta 1, right? And in fact, what I'm testing is null being, I have the notes here, null being beta 1 equal to 50,000 or not. But it's in thousands, so I want to check if 50 is within the confidence interval or not. But the value is 13.885. So beta 1 hat minus beta 1 divided by the standard error. And the standard error is basically, you know, it's going to be reported here on the regression model, 9.01. And I have negative 4.01. What is the degrees of freedom? We have 4 betas, like beta 0, beta 1, beta 2, beta 3, so 4. So we have 88 data points. My degrees of freedom is 88 minus 4 as 84. So my test statistics is negative 4.01. So if we have the 0.05, then the critical value is 1.987. The absolute value is 4.1, so it's way on the right side. Would you reject or fail? It's way on the right side. Is it in the confidence interval or not? Is my value of interest? Would you fail to reject or reject? It's way on the end of the tail, right? So we reject, which means adding a bedroom is not going to add 50,000 in expected home price. So it's like if the cost of building another room, or if the cost of within the same square feet, right? If the cost of making one room into two is 50,000, you wouldn't do it. Oh, where do I get the 4 subtracted? Here's what I get. How many parameters that I know of, right? These are the parameters I know of. So there are 1, 2, 3, 4 parameters that are fixed. So I have to fix 4 points out of 88 points. That means I have 84 points of degrees of freedom. I can't change the 88 points, but 4 points must be on the line, the averages. Okay? Because our claim is when we run the OLS, the averages must be always on the line. Okay? 4 points must be always on the line. Does that make sense? Okay, another test. The amount of square footage does not affect expected home price. What's our null? We go to square feet here. This is beta 3. What we are basically saying is beta 3 equals to 0 or not. If it is 0, then my claim is right. So that's the hypothesis test. Beta 3 being equal to 0 or not. And we have 0.123 as our estimate, minus 0. That's what we are testing. And then standard error is 0.013. And then we have the test statistics 946, but it is also on the rejection ratio. So we, again, reject. So rejecting this, it means it's statistically significant. The amount of square footage affects expected home price, which makes sense, right? Especially. Okay, these are two-sided tests. Another test. Another 1,000 square feet in lot size raises expected home by 2,000. We go back to lot size. Now we have in thousands, so another 1,000 square feet, right, in thousands. So what we check is the value we have here, 0.027, 0.00207 minus 0.02 with the standard deviation 0.0006. We have the test statistics as 0.117. Again, degrees of freedom is the same, 84. We have alpha 0.05. Now we have to reject again. So again, reject if t-value, I'm sorry, again, we reject if t-value is greater than 1.987. But is that the case? We have now 0.117. It's not in the rejection, but it's within the confidence interval. So we fail to reject this time. Okay, so in fact, another 1,000 square feet in lot size raises expected price by 2,000. That's a statistically significant claim. And one-sided test. An additional bedroom increases expected sale price by no more than 10,000. Oh yeah, that's right. Let me go back. This is our test statistics. Yeah, it is less than 1.987. You remember the two-sided test? We check if the absolute value is less than that value or not. And then if it is like, let me show you again. If it is here, right, we fail to reject. If the absolute value is greater than the critical value, then we reject. But in the very last two-sided test, the critical value is less than the absolute, critical value is greater than the absolute value of the test statistics. So we fail to reject. Okay, Alicia? Okay. Now, one-sided tests. An additional bedroom increases expected sale price by no more than 10,000. By no more than 10,000 means less or equal to 10,000, right? So it's a one-sided test. So what we are doing is whether beta 1 is less or equal to 10,000 or not, or beta 1 is less or equal to 10 or not, because it's in thousands. So we check the test statistics again, depending on the parameter we estimated. And then we have the value in question. So we have 0.427. If the critical value is 1.662, it is on the left side. So we fail to reject. So if it is 10,000, then I would go and have another bedroom, and it increases my price by 10,000. So if the cost of building another bedroom is 10,000, then I would build it because it's gonna give me a higher return when I'm selling my house. That's how I can conclude. Is my conclusion clear? Okay. Another one. An additional square foot increases expected sale price by at least 200. Now I go back to the square feet. This is my parameter, and 200 is 0.2 in thousands, right? So what I have is 0.123 minus 0.200, negative 5.92. Degrees of freedom is still 84. If we have alpha, we reject if t is less than the critical value. But is it less than critical value? Would you reject or fail to reject? Now, this is a one-sided test, not two-sided. So I don't have to look for the absolute value. So negative 5.292 is way below than 1.662, so I fail to reject. That means this claim is I'm failing to reject. So it must be, I cannot say it must be true, but it may be true, right? An additional square foot increases expected sale price by at least 200. It could be even more, right? But at least 200. It could be 300, 400, 500, but at least 200. So if you have a project that increases your square footage and you are paying less than 200, then you may want to pay, because an additional square feet increases the expected sale price by at least 200. So we are not rejecting this. Oh, we are rejecting this. I'm sorry, we are rejecting this. Okay. Me too. I guess me too. I said fail to reject, right? I get, yeah. I said, I'm sorry. My mind was thinking about rejecting, but yeah, I wrote here reject. So we reject. So if your project is basically costing you 200 or more, you don't want to really pay because you are rejecting that. You are not getting any return. Where did 1.662 come from again? This 1.662 is the critical value, where on the tail we have the probability 0.05. Let me show you how. Like t distribution, right? But we have t distribution with 84 degrees of freedom. You have this value as 1.662. Okay, so we calculate this value, where on the right tail we have the area as 0.05, because the other ways we have the 95%. That's how we build our confidence intervals. I was not testing you guys. Sorry about that. I told you I am not feeling well. So at some point I was confused as well, probably. So I apologize, right? I was not doing it with purpose. I humbly apologize. Okay, are the tests clear? How we are running them? Because in the problem set, I am asking you to run some regressions, and depending on the outputs, run these tests. And when you are running regressions, I want you to report the outputs, okay? When you are submitting your problem set number 1. I saw that some of you submit only the answers, but problem set number 2, when you are submitting, please submit your work. If you are running a regression, include the outputs and include how you are choosing betas and what you are testing with. Let me know and let me understand. So what we're gonna do is, right, I wanted to go over one other thing, but it would take 20-25 minutes. I'm gonna do that next time. And let me tell you though what I will be doing, how I will start next time. What I will be doing is, next time I'm gonna tell you how to test single linear combination of parameters. Or maybe I'll just mention in 10 minutes and we'll continue with that next time as well. So if you have a model like this, right, rather than Excel, let me do this very quick. If we are believing that your wage depends on whether you go to public school or private school, right, with experience, we may want to test the following. Is the difference between the wage difference between going to public school and private statistically significant or not? Because when we run the regression, maybe I should now go to my other screen. I'll just show you the regression model. So we have these betas. As you can see, the effect of private school, going to private school, is more than going to public school. But what if I want to test the following? What if I want to test if these two are equal or not? Or in other words, what if I want to test whether going to public school has the same effect or going to private school or not? But we are not only testing one parameter, but now we are testing single linear combination of parameters. Then what I'm going to do is I'm going to create another random variable, which is going to be the difference. So this is going to be like my delta. But I can still transform this into standard normal. I have my delta minus 0 divided by the standard error of beta 1 head, beta 2 head. I know what these two are, but the problem is I don't know what the standard error is. So I come up with another regression model. Here is my modified regression model. My modified regression model is now having delta as beta 1 minus beta 2. Look, I have beta 0, delta public, beta 2 public plus private, plus beta 3 experience UI. So what I did is basically, instead of beta 1, I write delta plus beta 2. So that means I have delta public, right, but also beta 2 public. So this is the same model, but writing down the new parameter rather than just beta 1 and beta 2. So what do I want to check? I want to check the following. If this is 0, then there is no difference between going to public and private. But however, if public gets an extra or lesser return, we can break that out on its own and see what that is going to bring us. So we're going to check now the new regression model, and we're going to check whether our new parameter delta equals to 0 or not. That's what we're going to check. So we run the new regression, we come up with the values, but more importantly, we find the standard error. And standard error will be reported by the Excel. So given this, we run the new regression model. Standard error reported by Excel is 0.05, and we end up with negative 1.4. This is a one-tail test. If n is large, then we can have the standard normal rather than the t-distribution. So are we going to reject or fail to reject? So it's negative 1.96. So our confidence interval is negative 1.6 to 1.96, and our value is negative 1.4. So it's within the confidence interval. So we fail to reject. So that means what? In our model, in this model, when you run with the new parameter to see if going to public or private school really matters. The data is showing us it doesn't really matter. So whether you go to a public school or private school is not going to change your wage statistically significantly. Okay, does that make sense? The process? This is the idea. And make sure you understand that process. You understand those tests. If you have any questions, feel free to ask me. When we meet next time, I am hoping that I can make on Monday. So let's try to do that. Let's try to do it on Monday, but I'm going to announce it. I will let you know again with my announcement. I'm going to publish another announcement. So next week is the midterm week, and I will talk about testing multiple restrictions in the first part, and in the second part I'll go over the midterm and what I'm expecting from you, and we will just go over the basic concepts again one more time, like a quick review. But if you have any questions you want to ask, you want me to cover during the live sessions, just let me know, email me. But then you will be taking the midterm next week. Get ready and make sure you understand what we have been doing. I'm not going to test you on Excel skills, but I will be testing you on the business econometrics part, right? How you interpret and how you kind of run the test and how you understand these assumptions or not. So it's about econometrics, not about the Excel. Assignment 2 is due on Sunday. That's right. So you will be running regressions and you will be testing some parameters, right? That's what the assumption number 2 is about. I'm sorry, assignment number 2 is about. I took some drugs to painkillers, so sometimes, right, if I don't make sense, I really apologize. It's showing the effects. Okay, any questions? By the way, I would like to thank Ryan for telling me that this session was not recorded, and it has been recorded. If you couldn't see it, please watch it, or if you would like to watch it again, just go over the examples we have been solving. These examples were relevant to your assignment, also to the midterm. And until I see you next week, next Monday, take care, have a good night, and please let me rest a little bit and then come fresh next week. Okay? Bye-bye, everyone. Good night and enjoy the March Madness.